Hello and welcome to Chapter 5 for the indefinite integrals and net change. So first let's evaluate the difference between a definite integral and an indefinite integral. A definite integral is a number or a value that represents a specific area which can be evaluated by the difference of the antiderivatives evaluated at b and a respectively. An indefinite integral is a function or a family of an antiderivative function that differ by a constant, which is usually denoted as c. To integrate a function, it must be continuous on the integral from a to b by the fundamental theorem of calculus. So here are some rules for indefinite integrals. When you have a constant, you can move it to the beginning of the integral, and when you have to add them, you can just simply add them. And when it's just a constant, it'll be the constant times x plus c, which is any constant. When you have x to the nth power, it becomes x to the n plus 1 over n plus 1 plus c, and when it's the integral of sine, it becomes negative cosine x plus c. And when it's cosine x dx, it becomes sine x plus c, and secant squared x becomes tan x plus c. Cosecant squared becomes negative cotangent x plus c, and secant tangent becomes secant x plus c. And cosecant times cotangent becomes negative cosecant plus c. And if we have a formula for a general antiderivative, it is only valid on an interval such that the integral is definite, or such that it's defined. So if you are taking the antiderivative of f of x over 1 over x, the interval a to b cannot cross over x equals 0. So basically, if x can't equal a certain value that's within the integral, then you cannot evaluate based on the fundamental theorem of calculus. So let's look at an example of evaluating an indefinite integral sine x over cosine squared x dx. So first, we use the trig identities to rewrite it as the integral of 1 over cosine x times sine x over cosine x dx. And then we can simplify it to secant x times tangent x dx, and a derivative of secant x is secant tangent. So when we plug that in, it becomes secant x plus c. So for the next example, we'll find the exact value of the integral from 0 to 8 of x plus 5 cosine x dx. So we're going to use the fundamental theorem of calculus part 2, where we'll plug in f of 8 minus f of 0, the antiderivatives. So the antiderivative of this integral is x squared over 2 plus 5 sine x, evaluated at x equals 0 and 8. So we just plug in those values, and we get 36.9468. When you plug this into the calculator, make sure that it's in radian mode. So net change theorem is the integral of the rate of change, which is the net change. So that's denoted as the integral from a to b of the antiderivative f of x dx, which equals the antiderivative evaluated at b minus the antiderivative evaluated at a. So for problems like these, we'll consider volume, which is the flow rate and the net change in volume. So for example, if oil leaks from a tank at a rate of v prime of t gallons per minute at time t, what does the integral from 0 to 120 of v prime of t dt represent? So that represents the net change in volume. In population growth, like the integral from t1 to t2 of dn over dt, so the difference of this antiderivative equals the the net change in population. So another example, if d of n over d of t is the rate of growth in a city in number of people per year, 2 years after 1900, what does the integral from 50 to 65 of dn dt represent? So the 50 to 65 represents the year of 1950 to 1965. So when we evaluate these numbers, we get the net change of the population from that time interval of 1950 to 1965. So here's an example with velocity. So with displacement, t of 1, the integral of t to 1 of t of 2 of v of t dt equals the net change in position, and distance traveled equals the integral from t1 to t2 of an absolute value of vt dt, which equals the total area. So here's another example of a velocity function. V of t equals t squared minus t minus 6 in meters per second is given for a particle moving along a line. So first we'll find the displacement of the particle in an interval from 1 to 4. So when we evaluate the antiderivative of this, we get t cubed over 3 minus t squared over 2 minus 6t evaluated at t equals 1 to 4. And when we plug in the interval values, we get negative 4.5 meters. So the particle moves 4.5 meters to the left, since left would denote a negative position and right would denote a positive one. Next, we'll find distance traveled by the particle during the given time interval. So this time we'll be finding the antiderivative of an absolute value function. So when we figure that out, it becomes t cubed over 3 minus t squared over 2 minus 6t evaluated at t equals 1 to 3. Then when we plug that in, we get 61 over 6, which equals 10.17 meters, and that's the total distance the particle travels from 1 to 4. And obviously that would be positive since it's the absolute value. So here's an example with the net change in velocity. So what does the integral notation for net change in velocity look like? So basically it looks like if a of t equals v prime of t, then the integral from t to t1 to t2 of a of t dt equals v of t2 minus v of t1, and f of a t dt equals v of t plus c. So an example of using this, the acceleration function in in meters per second squared and the initial velocity are given for a particle moving along a line. So first we'll find the velocity at time t. So basically to do this, we just find the antiderivative of the function, which becomes v of t minus v of 0, so it just becomes 5t squared plus 4t plus 5. Then we'll find the total distance, which again we just plug in the values and we get negative 4 plus or minus the square root of 6. And the total distance traveled would be 416 meters. Thanks for watching.